Hello everyone, it's Momo Kell. You're welcome back to this page. So we are still dealing with sequences and series. In our last video, we talked of the definition of sequences and series. We talked of the general term. We saw what an arithmetic progression was. We saw the arithmetic mean, the common difference, the sum of an arithmetic progression, and we also saw the end term of an AP. So today we are looking at geometric progression, which is the second type of progression in a sequence. So let's look at our definition. What is a geometric progression? A sequence is said to be in a geometric progression if and only if there is a constant number multiplying a previous term to get the preceding one. For example, if you are given this sequence, that can be said to be in a geometric progression because you can observe that there is a multiplication of 2 from the first term to the second term, and from the second term to the third term there is also a multiplication of 2. Therefore, multiplying 2 has then become a rule for obtaining the next term, making it to be a geometric progression. If we take, for example, this sequence, here we can also see that there is a multiplication of 1/3 from the first term to the third term, and from the first term to the second term, and from the second term to the third term, there is a multiplication of 1/3, meaning that it is constant, making it to be in a geometric progression. So the constant number multiplying the individual terms is usually known as the common ratio. It is denoted by R. So from this common ratio, we can consider whether a sequence is in a geometric progression or not. By saying that, if there is no common ratio in a sequence, then the sequence cannot be said to be in a geometric progression. Take for example, if you are asked to look for the geometric progression of this term, apart from observing it and seeing the multiplication, you can also do the second term divided by the first term, or still the third term divided by the second term. You can even say the fourth term divided by the third term. It should continue, it should be constant to be called common ratio. So when you do this, to be sure of your answer, when you do second term divided by first term, to be sure, you should also do third term divided by second term. So now that we know what a common ratio is, let's look at what we call the end term of a GP. End term is usually denoted by UN or TN, similar as the one in arithmetic progression. So here, from this term or from this expression, we can get any other term of a geometric progression. To get this end term, we have to establish a one-to-one correspondence between the geometric progression and the arithmetic and the set of natural numbers. So how do we do to have our geometric progression? If the first term of the geometric progression is denoted by A and our common ratio R, we know that to obtain a preceding term in a geometric progression, we multiply the previous term by the common ratio. If now we have the first term to be A, then the second term will be given by A times R, which is first term times common ratio, giving us AR. Then the third term is said to be the second term times the common ratio, which is AR squared, and it continues so on so forth. Now, when we establish the one-to-one correspondence with our set of natural number, which is 1, 2, 3, the n number, we can have this. So now here we consider the powers. We are working with the powers. So we make the powers to become the natural corresponding number minus 1. It will give us this. We're going to have AR to the 2 minus 1. It still comes back to AR. We're going to have here AR to the 3 minus 1. And then AR to the n minus 1. So here, this is said to be our n term. It is said to be the n term of a geometric progression. That is, from this expression, you can have any other term in a geometric progression. A here stands for the first term, R for the common ratio, and n for the term we are looking for. Now let's look at what we call geometric mean. So the geometric mean, let's take for example 3 consecutive terms of a GP. When we talk of 3 consecutive terms of a GP, when we say they are consecutive, it means that there must exist a common ratio. When they are consecutive terms of a GP, we must precise. If maybe it is said they are consecutive terms of an AP, then it is instead a common difference that must exist between them. But here we are talking of consecutive terms of a GP, and therefore, since they are said to be consecutive, the ratio must be the same, to be equals to this. And if we solve this, we're going to have y squared equals to x², which gives us y squared equals to the root of x and z, and y is therefore said to be the geometric mean of x and z. Let's now move to the sum of a GP. So when we talk of sum of a GP, we mean the addition of the various terms in a GP. It is denoted by Sn. So to get a formula for Sn, we need to have the series first of all. Maybe if we just use our GP, AR squared, ARn minus 1. This is our GP. This is the GP we had previously. This is our GP. Therefore, the sum of this GP, or still the series of this GP, will be A plus AR plus AR squared plus dot 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 plus ARn minus 1. So this will be the sum of our GP. So now we are looking for a formula. I'm trying to establish a formula so that I will not have to add the terms continuously, since it is even infinite. So I will multiply this sum by R. It will give me Rsn, R times this, then AR plus AR squared, R times this, plus dot dot dot, you continue adding, plus multiplying, plus AR to the n minus 1, plus AR to the n. Here it stands for R times the term coming before AR to the n minus 1 is AR to the n minus 2. If you want to place it, to place everything, then you have an A to the R n minus 2. So it will give us this, and then R times this is AR to the n. So we can take this equation to be 1 and this to be 2. If I then do equation 1 minus equation 2, I'm going to have Sn minus Rsn, which will be equal to a minus, not here, there is no a here, so it will be a. I'll keep my a. Ar minus ar is 0, ar square minus ar square is 0. If I do a to the rn minus 1 minus a to the rn minus 1, 0. Then 0 minus a to the rn will give me minus a r to the n. So this is the sample I am left with. I'm looking for Sn, so let me factorize it here since it is common. It will give me n into 1 minus r equals to, I do the same for here. It will be a into 1 minus r to the n. Therefore Sn will be equals to a into 1 minus r to the n, all over 1 minus r. So this is said to be the sum, the formula to get the sum of a GP. So here, from here, two cases can arise from this formula. Two cases can arise. The case where R is greater than 1 and the case where R is less than 1. Now, if R is less than 1, for R less than 1, this formula will be used. That is, it will be 1 minus R to the n and 1 minus R, since R is less than 1. But in the case where R is greater than 1, therefore, these places, they will exchange their places. For example, it will become Sn equals to a into r to the n minus 1. They will change the places, divided by r minus 1. Since r is greater than 1, then 1 cannot subtract r. We are going to end up with a negative number. So this will become our formula. Now let's finally look at the convergence of the infinite geometric progression. So when we say a GP, a geometric progression, is convergent, we mean it's an infinite geometric progression having a sum, and that sum is regarded to as sum to infinity. So when an infinite geometric progression has a sum to infinity, then it is said to converge. For example, if we maybe say, let's take Sn, a into r to the n minus 1 on r minus 1. This is for r greater than 1. Let's see if it can converge. We are trying to see whether for r greater than 1, the geometric progression converges. Now, this Sn still equals to a r to the n on r minus a on r minus 1 minus a on r minus 1. Now, if n tends to 0, then r to the n if n tends to infinity, then r to the n here will also turn to infinity. And since as n continues adding and adding, Sn, which is the sum, becomes very, very large, therefore the sum to infinity cannot exist, and therefore the GP cannot converge. Therefore there is no sum to infinity. A GP does not converge for r greater than 1. But then if r is less than 1, then Sn will be equals to a into 1 minus r to the n on 1 minus r. Here, when n tends to infinity, r to the n turns to 0, because it is 1 minus r to the n. So when n tends to infinity, r to the n here turns to 0, and therefore the sum to infinity will therefore be equals to, if r to the n here turns to 0, it becomes 1 minus 0, and a times 1, which will become a on 1 minus r. This means that a GP can converge if and only if r is less than 1. If r is less than 1, then the sum to infinity exists, and therefore the GP converges. So that will be all for this video. Hope you have learned much today. Thanks for watching. Don't forget to like and subscribe so you can follow me. And next video, we are going to solve some example or some work examples on geometric progression, arithmetic progression, anything on sequences and series. Thank you.